Hi everybody, this is Max from LED Tonic, and today we're going to talk about PPFD. So what is PPFD and how is it measured? Well, we talked about this briefly in our previous video, but PPFD stands for photosynthetic photon flux density and is measured in this unit, micromoles per meter square per second. A PPFD value tells us how intense light is at a certain spot, and to measure this accurately, we use a quantum sensor. This sensor measures how many photons that hit the top of the sensor each second and translate that to how many photons that lands on a whole square meter each second. This can be rather confusing, and you might ask yourself, why do I need to know the value of a whole square meter when you only care about the area of your plant? And the short answer is you don't. Although the unit micromoles per meter square per second defines the value of a whole square meter, this sensor only takes a spot measurement, and this spot measurement is all we really care about. This is industry standard, and this theory is applicable to any grow light or test where PPFD is being measured. So, what lighting levels should we provide our plants with? Well, we've talked about this briefly in a previous video, and we'll expand on it even further in an upcoming. But in short, clones, cuttings, propagation, and seed starting require the least intensities. Small herbs and leafy greens want a bit more, and we have high light plants that will prefer slightly different intensities depending on their development stage. These recommendations are not end-all be-all, they are just general guidelines. Basically, there is a minimum intensity that we want to be above. This is called the light compensation point. If plants get less light than this, they'll slowly die. If they get more light than this, they'll grow. Photosynthesis is increased more or less linearly with irradiance levels or light intensity up to a certain point where it's starting to give diminishing returns. To simplify and generalize, this is somewhere around 400 to 500 ppfd in many of our popular plants. In other words, increasing light intensity from 200 to 400 ppfd will double the rate of photosynthesis, but increasing or doubling from 400 to 800 ppfd will not. On the other side of this chart, we have the light saturation point. Giving your plants more light than this won't have a positive effect or increase the rate of photosynthesis. Instead, it can actually hurt or damage the plant and lower the rate of photosynthesis. Both the light compensation point and the saturation point is individual in all plants. Low light plants have both a lower compensation point as well as a lower saturation point. The saturation point is also dependent on what development stage a plant is in, which is why we want to give our seedlings less intense light. We want to be somewhere between the compensation point and the saturation point to make our plants happy. Where you want to be depends on what plant you are growing and your desired results. To generalize this and simplify it even more, most adult plants would be happy if we give them 100 or even better, 150 ppfd as a minimum. At 400 to 500 ppfd, this is considered a sweet spot where light intensity is considered high, but most light is still utilized by the plant. Pushing past 500 ppfd, we are reaching very high intensities, and above 800, 900, this ballpark somewhere, the returns are rather slim even in high light plants. There are a bunch of other factors that play a role in the rate of photosynthesis, such as temperature, airflow, carbon dioxide levels, humidity, nutrients, and watering schedule. at very high lighting levels. Photosynthesis is limited by the availability of carbon dioxide in the air, and increasing this level, the carbon dioxide levels, we can move the light saturation point even further. After all, plants follow Liebig's law of the minimum. This law states that plant growth is dictated not by the total resources available, but by the scarcest resource, the limiting factor. Blasting your plants with high PPFD levels will be wasteful if light isn't the limiting factor. When growing kitchen herbs, small leafy greens or microgreens at home, we can achieve great results with 150 ppfd. While 150 ppfd is nowhere near the light saturation for kitchen herbs, it will be good enough for what most people are trying to achieve when growing this type of plant. As example, we've grown basil ourselves with everything between 150 and 600 ppfd with good results. For most situations, it isn't economically viable to aim for 600 ppfd, which also could be pretty close to the saturation point for basil, and instead 150 or 200 ppfd will be just fine. On the other hand, tomato, pepper or cannabis plants won't thrive in this low intensity, as all three of these are considered high light plants and have both higher compensation points as well as saturation points. They would survive and grow with 150 ppfd, but they wouldn't thrive. This is especially true during flowering stage, when a lot of light and energy is needed to produce fruits and buds of both good quality and quantity. With 150 ppfd, or even worse, 100 ppfd, they would most likely grow thin and tall, as they would be reaching for the light source, trying to increase the light intensity themselves. In extreme cases, the plant's long and thin branches can even break from the weight of its own fruits or buds. So, giving plants less than their ideal requirement will hinder growth potential and also harvest. The plants will not grow as big, fast, or with as good quality as they could, and will not bear as much fruit or buds as they would if all of the plant's requirements are met. Ideally, every leaf should be illuminated and fully stimulated for best results, but it won't be a catastrophe if one or a couple leaves are getting less intense light. As example, here's a tomato plant that has outgrown its light source a while ago, but it is still growing compact and even producing flowers. It is getting around 600 ppfd in the very middle, around 80 ppfd in the outer edges, and between 5 and 25 ppfd on the shaded leaves. It is not ideal, but we still have a decent looking tomato plant. When measuring light intensity produced by the sun, we can move the sensor several meters sideways and still read the same light intensity. This is because our sun is a giant light source that is also extremely far away. Moving the sensor sideways won't change the distance and angle enough to produce a noticeable difference. Measuring a lamp is quite different, as the light source is a lot smaller, but also a lot closer to the sensor. Moving the sensor sideways or closer to the lamp will result in vastly different readings. Most lamps produce the strongest light right below them, and intensity decreases the further we move away from the lamp's center spot. To understand how a lamp performs and how large area it can cover with a certain intensity, light intensity must be measured on several spots below the lamp, and preferably also at multiple heights or distances. Different light sources can also spread or focus light differently. To know how a lamp performs, it must be measured. Two different lamps drawing the same amount of power and putting out the same amount of light can produce vastly different light intensities over a certain area. Reflectors and focusing lenses can guide and focus the light, making it more concentrated and forcing it to land just where we want it. Lamps with narrow focusing lenses, 90 degrees or even narrower. This one is 30 degrees as example. Force the emitted photons into a small area and usually resulting in very high PPFD in the center spot underneath the lamp, but low PPFD a foot away from the center. These can be both good and bad. It benefits a small grow area, but not a large one. It can also make a lamp appear more powerful than it actually is if the PPFD value presented by the lamp's manufacturer is a center spot value. More on this when we talk about light footprint maps. Here's a good example and comparison. This generic household bulb is rated around 800 lumen and draws almost 10 watts. According to IKEA, this grow light also draws 10 watts and puts out 800 lumen. They are both hanging at the same height, 10 inches, considering where the diodes are actually placed on both bulbs. Plugging them in one by one and reading the PPFD below them. This bulb produces 35 PPFD and the IKEA lamp is at 700. One lamp is fitted with narrow 30-degree focusing lenses and the other lamp is fitted with a milky and diffusing cup. Focusing lenses will gather most of the light and direct it over a small area. A milky cover does the opposite. It spreads light and sends it in every direction. To clarify this even further, here's a couple of drawings that describe the difference that optics or reflectors make. In these examples, all lamps draw the same amount of power and emit the same amount of light, or in this case, lines. All of them are also hanging on the same height. Starting off with a light source that emits light evenly in all directions. This could be a compact fluorescent or an HPS bulb without a reflector. Moving on to an LED lamp. LEDs without optics or reflectors will naturally emit light in 180 degrees. Light will not be emitted with an even intensity in 180 degrees. Instead, the greatest intensity is produced right below the lamp in the center spot underneath it. As we move away from the center spot, light will become less and less intense and reach 0% at an angle of 90 degrees. Continuing with a lamp that has a 120-degree lenses, we can see how the photons or lines are getting less and less space between them. The same amount of total light is suddenly confined over a smaller area and light intensity is therefore increased. Moving on to the last lamp, a lamp with 30-degree focusing lenses. The lamp's light is now packed below it and the light intensity is several times higher below the lamp compared to the other lamps. This is why the IKEA lamp's light footprint is so different from this generic bulb's footprint, despite having the same power draw and total lumen output. The efficiency of the diodes also plays into this effect slightly, but this is a topic for another video. Taking one center spot measurement below the lamp will tell us how strong light is right below the lamp, but it won't tell us how large area a lamp can cover or how the value changes if the distance is increased or decreased. Even this phone's flashlight, tiny flashlight, even with this flashlight, we can reach intensities of over 500 ppfd when held about an inch from the sensor. 500 ppfd is a great intensity for adult fruiting plants, but moving the phone slightly, and we quickly see that the area covered is tiny. Also, increasing the distance slightly, and we'll quickly reach intensities more or less unusable to almost any plant. In other words, despite producing 500 ppfd at a certain distance, this lamp is rather useless to grow plants with. This is why a detailed PPFD map is important to be able to evaluate a lamp's performance and to hang a lamp at the correct height. Taking our Z5 LED grow light as example, in a 4 by 4 feet large space, reflective space with mylar walls at 2 different heights, we can see that the center spot intensity, or that the light intensity, is greater when the distance is shorter between lamp and ground compared to when the distance is increased, because then we have a greater spread of light. And measuring carefully with a quantum sensor, we can see that the center intensity is decreased, as well as the outer edges have a slight increase in intensity. I want to share a couple more examples with you that I found by searching on Google. I have covered each lamp with a box here, as the specific lamp isn't what's important. We are also not looking at the specific intensities produced by each lamp or comparing which lamp is better than the other. I only want to share my thoughts on how to read a PPFD map, what it should include, what to look for, and possibly what to look out for. Starting with the two maps in the top left corner, we have a cone-shaped design. The map to the left has a recommended height of between 12 and 20 inches. It also tells us that the lamp covers 2.8 square feet, which translates to a diameter of 22.5 inch or 57 centimeters. Looking at the other map, it has 3 different height recommendations, one for germination, one for vegetative, and one for flowering. We don't need to have a deep understanding of PPFD to hang these lamps at the recommended height. But how can we compare these two lamps? How do we know which one is best? How can we know what intensity is produced in the center spot and in the outer edges? The map on the right-hand side doesn't even state how large area it covers. Moving on to this type of lamp that I also call 1D maps, the center spot intensity is stated and on multiple heights. We can only see how the lamp is performing in one direction or dimension. This map is trying to tell us something about the core coverage, but I have no idea what it's trying to say. Moving on to the second 1D map, which has the same type of design, just different values. This one is also trying to say something about the core coverage, but a bit differently. I still can't figure out what. Looking at the third and last 1D map, which also has the same design, it has included some PPFD measurements in the other direction as well, although it's only included on one height. Should we want to use this lamp on any other height than this, we really have no clue about what intensity to expect as soon as we leave the center spot. Also, this type of map, 1D map, can be extra skewed if the lamp has a rectangular shape and measurements are only shown in the direction that is favorable to its shape. Taking this T5 fixture as an example that we've measured in a previous video, it is rather clear that its light footprint is extremely poor, but also that it has an oval shape. It would be misleading to only show this measurement at 5 inches or 12 centimeters roughly from the very center. in this case 200 ppfd, and exclude the measurements in this direction, also at the same distance from the lamp's center, but only about a tenth as intense. Placing a plant below the lamp here will only give it a fraction of the light it needs to produce good results, if 150 ppfd is the threshold. The lamp will really only cover an area of this size with a minimum of 150 ppfd, and that would be impossible to tell if we're only including 1 or 2 spot measurements on the PPFD map. Also, on all of these 3 1D maps, 24 inches or 60 centimeters seems to be the so-called perfect hanging height. On the first map, that results in 884 ppfd, on the second map 260 ppfd, and on the third map 187 ppfd. It's rather unclear what the thought is behind this, if there even is one. Moving on to the last example that also looks a bit different. I call this type of map for 2D maps, as we are given a bunch of measurements in both directions, but unfortunately only at one height, or I would call it a 3D map. At the first glance, this looks detailed and informative, but as we saw earlier in this video, a lamp performs best in the center spot right below it, and with decreasing intensities the further we measure away from the center spot. Considering this, we have 433 ppfd in the center spot, and then it falls down to 119, but then it rises up to 159. This is a rather strange pattern in my opinion. Also, this spot measurement is almost twice as high as this, which it could be if the lamp was hanging a bit tilted when it was measured, but then these 2 measurements would also be a lot stronger than these 2 measurements, and they aren't. Also, somehow this spot measurement is weaker than this corner measurement, and I have never really seen that happen before on any lamp. So what I'm trying to say here is that we must spend an extra second and really look at the numbers. If they don't make sense, there's a good chance that the lamp doesn't perform like the map displays. And I'm not saying that this map is fake or that the numbers are untrue, but I can't really see a logical reason for this type of pattern. Comparing all these maps to our standard PPFD map, it looks a bit different. Starting off, we've included the size and shape of the lamp, both on the side of the map as well as on the map. A nice feature that hopefully makes it easier to put everything into perspective. We've also stated what type of area the lamp has been measured in this case a 3 by 3 foot or 90 by 90 centimeter reflective tent. We display measurements in both directions as well as on 3 heights. 12 inches, 18 inches, and 24 inches, or 30, 45, and 60 centimeters. The 3 heights that we think are most useful for our lamp. The measurements from all 3 heights are stacked on top of each other, and we've understood that this can be difficult for some to read, so we've come up with a new design that looks like this, where all 3 heights are laid out. Looking at the previous map and these 3 measurements as example, 131, 169 and 173, we see that it is the exact same numbers, it is just a different design. And hopefully this gives a better overview. To summarize the topics of PPFD and PPFD charts or light footprint maps, I would once again like to highlight the importance of a true and accurate map from grow light manufacturers. Without detailed maps, there's no way to know how a lamp performs. This is important for you as a potential shopper to find the right lamp for your grow area and your plants. As a comparison, imagine if your car's speedometer looked like this, or in best case, like this. You really don't know how fast you're driving unless you're driving at the exact speed that's listed, in this case the top speed. And this could be compared to only including a center spot intensity below a lamp. So making sure that the light footprint map is at the very least 2-dimensional 2D, as in showing the PPFD values both vertically and horizontally, is strongly recommended. Ideally, you'd like to see the PPFD values in all directions and on multiple heights, so that you can determine if you have good enough intensity and coverage. Knowing these numbers is essential for you to buy the right lamp, to set it up correctly, and to understand how large area it can cover. For our own Z5, we recommend it to be used in a 2x2 foot grow area for best coverage. We see here on this 3x3 foot light footprint map that the numbers within the 2x2 foot space are decent. And they are even higher if measured in a 2x2 foot tent compared to this 3x3 foot. To clarify, here's a light footprint map of the Z5 measured in a 2x2 foot tent, and we see right away that because of the tighter and smaller space, the light is even better concentrated and the PPFD values are higher across the board, but especially in the outer edges. As the same amount of light is concentrated over a smaller area, light intensity is increased. Here's a quick close-up for better visibility. The Z5 would work in a 3x3 foot tent as well, but the plants or leaves farthest away from the center would receive less than ideal light intensity, assuming they are high light intensity plants. Another way of looking at this is to arrange the plants underneath the lamp to match the PPFD levels. As example, we can place 1 or 2 high light plants, such as flowering cannabis or fruiting peppers, centered under the lamp. Off center, we can place a younger plant of the same species or plants with lower light recommendations, such as a basil plant. As this plant is most likely at least 6 inches or 15 centimeters lower than the mature and adult plants in the middle, I'm drawing this circle on the second map to match the distance better. Also, these 2 large circles could represent several smaller pots instead of 1 large. Lastly, at around 24 inches or 60 centimeters from the lamp, we could use the outer edges and corners for seedling and germination. With this setup, we have utilized the whole space in a 3x3 foot tent and all plants are happy. The same principle can be used in a 2x2 foot tent. In this case, there's 3 tall but well-trimmed adult pepper plants in the back and an avocado in the middle to the right that never seems to stop growing leaves. It's creating partial shade for the Mizuna and cress microgreens in the middle that also looks just about ready for harvest. At the bottom there's some dillweed, a mango plant and a lemon plant. Both the mango and the lemon are slow growing and doesn't seem to mind the slightly lower intensities. All in all, a good setup with great variety. Or we can do like this customer and put all focus on 1 large highlight plant, in this case a cannabis plant. Alright everybody, that's it for today's video and I hope you learned a thing or two. As always, never hesitate to reach out if you have any questions, need help calculating your lighting needs or setting up your grow. And until next time, happy farming.